This is again the DS Incubator on the series about exploring data with the tidyverse. And this session is going to continue what we started last meetup, not last week because I was on a vacation. We started with the idea of typical values, how to explore typical values, the most common values in a data set. And we didn't have time to cover what I would like to cover today: unusual values, outliers, and missing values. So the objectives today are these: to explore outliers analytically and also through a plot in which we're going to zoom in to notice those outliers. Also, we're going to think about when it's correct or not to transform outliers into missing values, and having reflected and considered, for example, that the reason was a data entry error, then I'm going to convert them into missing values. So we're going to transform errors into missing values. And then we are going to convert those missing values into a logical variable so that we can do something like sum the number of errors that we have, the number of missing values that we have in the data set. So those are the three main objectives of today. From the conceptual point of view, as usual, the meetup notes are in the associated repository at ds.tidyeda for exploratory data analysis. And the folder number 5, unusual and missing values, is the one that contains the notes that I'm going to be covering today. So I'm going to move this to my right. And today, because an additional goal is to also beyond the concepts that we're sharing on a side, as a side effect, we're also kind of learning how to use the tidyverse. So to slow myself down a little bit when I speak. Today the examples are degraded, so I'm going to be typing some things as I speak. So we're going to be using the tidyverse, of course. So I'm going to run library tidyverse so that I have all the packages attached. The ones we're going to be using today, as we did last time, are ggplot2 and dplyr, but the tidyverse comes with a bunch of other packages. And in particular, the ggplot2 package comes with a dataset called diamonds, which contains a bunch of rows. And I would like to kind of focus on the variables that we're going to be exploring today. So before I complete this blank space here, I hear on the background a hand up. Go ahead. Who was that one? Did I hear a hand up? Maybe not.
CJ just left the call.
Ah, okay. Maybe that was it. Thank you. So, if we have a data set and we want to focus on a bunch of columns, in this case, the columns price, character, X, Y, and Z, we can use the function select, as we learned a few meetups ago. And now, we have the same data set, except that we are focusing just on those columns. So one thing that might be worth refreshing is what those columns are. So I'm going to do !diamonds to get the health file of that data set. And the developers have been kind enough to define the different columns. Weirdly enough, it's not compulsory to define the column names and tell the user what they are. But in this particular case, we have that information. So just as a refresher, a carat is the weight of a diamond. The price is self-explanatory, and then X, Y, and Z are different dimensions. So basically the length in millimeters of different dimensions of the diamond. So those are the variables that will be more relevant for this particular meetup. So this call here to select those columns gives us a little bit of an overview of the kind of data we'll be working with today. So, okay, let's get started by exploring outliers. And before that, we're going to define them as they are defined in the book. Basically, the idea of an outlier is something that is unusual in the data. Before we explore usual data, now we are focusing on the unusual data, on the complement of that. So the idea is that, there is a bunch of data that creates a pattern somehow, and then there is these few observations that are not fitting into that pattern. That is the outlier. And it is possible that they are data entry errors. Not always, of course, and that's something that we have to think about. But in the case of today, actually, we are going to explore them and realize that they are indeed data entry errors. So how do we do that? So first of all, I wanted to show you one plot that gives us a hint about the presence of outliers, although that hint is kind of subtle and even surprising in a way. So we're going to be using that diamonds dataset. Remember that the ggplot function has a first argument called data, so we can call that explicitly like this, or because we are so used to it, we may just remove it and call it implicitly. So we're going to be exploring the diamonds dataset with this plot. In particular, we want to do the geometric representation of the data that we want. In this particular case is a histogram that will be useful to explore data on the sides of the distribution. So let me show you what that is in a moment. The geom histogram and all geom functions have a mapping argument, which also you can not call explicitly if you want, and it takes a function called AES for aesthetic, and that function will kind of take arguments so that we can tell ggplot2 what mappings we want between the data and the plot. So in this case, the x-axis, and this is a little bit confusing, sorry, but it is what it is. So the x-axis of the plot is going to take values from the y variable of the data set. So x equals y in this case. And in histograms, we learn that there is a very important argument that is optional, but usually important to explore, which is the bandwidth, the beam width. So beam width. Usually, you come to, so if you don't use beam width, ggplot2 will give you something, but then by exploring the data, you will probably realize that there is one particular beam width that is the most useful in helping you answer the specific question that you have in your head at that time. So here is the plot. And the one observation that we can make is that, we see a bunch of data here towards the left of the plot. And it's surprising that there is so much white space here to the right. Actually, it's not white space. There are some data there, but that is exactly what I was saying before. That's a subtle hint that the fact that the x-axis is so empty in a way, like so much white space on the right, is giving us a hint that maybe there are some data that we don't see just because the plot is not at a good scale to see those data. Think that we're counting in the order of 30,000 units of this variable, right? And observations of this variable. And here to the right, we may have one or two values that are not very common, and thus they don't show up at this scale. So the one thing that's the first hint for an outlier in this particular plot. There is, of course, other ways to explore outliers. This is one. So one thing we could do is try zoom in so that we hopefully see what's going on in there. And this is surprising because ggplot2 in general adjusts the axis automatically kind of to fit the data in a useful way. So that's why it's, what's going on there? So let's zoom in. So there is a couple of ways to zoom in. The one that preserves the data is this one. It's calling, basically we are going to be using the same function that we used before, ggplot, then geom histogram, but now we are going to adjust the plot by adding a new layer where we explicitly set the coordinates of the x-axis. So the function in ggplot2 is called coord Cartesian, and it takes a couple of arguments. One to control the values of the limit on the y-axis, and another one to control the limits on the x-axis. So in this particular case, we want the ones on the y limit. So the argument is called y_lim. And it takes a vector, actually, of two values. One is going to be the minimum value that we want to see in the plot. In this case, we choose 0. And the second one is the maximum value that you want to see in the plot. So for the y-axis, the limits that I want to set are the minimum 0 and the maximum 50. So note that the default here is plotting 30,000. So we're going to zoom in into only the, the y-axis up to 50. So let's do just that. So let's run this code. And now you can see that the top of the plot is kind of cropped, right? But because we have zoomed in into the lower part of the plot, now we can see that, around 60, around like 30 something, and around like close to 0, we have some observations. It's just that there are so few, less than 10, that when we scale the plot to show us 30,000 observations, then, or 30, the count up to 30,000, then those values disappear pretty much, right, to our eyes. So that's the first then way to observe outliers via this histogram. So that's what we did. But note that the plot looks cropped at the top because, and that's a good thing because it's suggesting that the data continues on top of the plot. This is different to this other way, in which I'm going to show you now, to zoom in into a plot. And it's important to know the difference because this second way is lossy, basically loses data because it zooms in by cropping the data set itself before it creates the plot. In the previous case, in the one that I showed you before, the one that we are looking at on the screen, we first plot without cropping any data. So the data remains the same, the data set remains the same, it's just the plot that changes. But in this second case, we are going to be using another function that is called ylim, and I think it's an important thing to kind of know because sometimes, for two reasons. One, because sometimes it is what you want, to just drop everything that is outside those boundaries. But also sometimes because it's kind of misleading argument, more intuitively. So I think that ylim is a more intuitive name for what we want to do. And if you scroll through the reference section of the ggplot2 package on its website, you may find this function and think, okay, that's what I need, and then think that that's the only option you have, but then be frustrated because you are losing data. And how do you know that you're losing data? Well, not only because you would probably expect more data here at the top that you don't see, but also because you get a warning. So ggplot2 will not drop something without giving you an informative warning. So it's telling us that some missing values have been removed. That will probably sound a little puzzling, but then with a little thinking and exploration, you will probably realize what's going on. So okay, so ylim is one way, a lossy way, and then core Cartesian is another more conservative way. Okay, so now let's explore those outliers analytically. Maybe I think one thing that could be useful is to recover the previous plot here on the screen, because basically what I want to focus is now on this big chunk of data in the center and compare it with the data lower than this and greater than this. So basically values that are less than around 3 and greater than around 20. So that's what we're going to be exploring in a moment. Okay, so let's go here. So the dataset we are working with is what I'm going to be completing here is still the full diamonds dataset, but this time I'm going to be filtering only the rows where the variable y has values either smaller than 3 or greater than 20. So that is what this line 64 is expressing, right? So let's filter, let's pick only rows where y is less than 3 or more than 20. And then to get a better view of what we have just accomplished, we are going to focus just on price X, Y, and Z columns, and then we are going to arrange the data set by the values of Y in increasing order. So I am going to assign all of that to a new object called unusual. So then if we call the object unusual, we can have a quick look at what the data looks like. And there is the first hint, or the hint that we need to realize that the values are data entry errors. Why? Well, because notice how, for example, the price of these diamonds is significant, right? So this diamond is costing, $5,139, but its dimensions are 0, like 0x, 0y, 0z. So the 3 dimensions of the diamond are all 0. So it's an inexisting diamond that is costing us a lot of money. So obviously that's a mistake. And the same thing for all other values here. So, and then the other hint, here we have values in the last 2 rows, but notice how these are huge. I see how this diamond, for example, this last one, has one dimension that is 58.9, almost 59, almost 60 inches in one dimension. That is like a gigantic diamond. And although it is expensive, it's probably not as expensive as we would think for such a huge diamond. I mean, it's in the order of the tens of thousands of dollars and not in the order of, you know, hundreds or of thousands of dollars. So this little analytical summary that we've done of our data, or subset of data, tells us that this is just data entry errors, and we would probably want to just remove those specific observations of variable y, and because that's what we are exploring right now, the variable y. But obviously there is errors in other variables too. But just focusing on the variable y, we can tell now that that was a data entry error, and we could replace those zeros and that, say, you know, 31.8 and 58.9, we could replace them with NAs, just missing values. But then the row remains, so the rest of the observations that we measure on the properties of that diamond are still there. It's just that specific column that is now kind of nullified by transforming it into missing values. So that's what we're going to be doing next. So let's move there. So the way in which you would approach this issue then is, you know, you repeat your analysis with and without outliers to notice if there is an effect. So if removing the outliers that has no effect in your results, whatever your question, your research question is, then it's kind of okay to remove them by, you know, transforming them into missing values, and you don't have to give it too much explanation. But if removing the missing values does have an effect, then, I mean, if you're gonna remove them, then you have to have a very good reason. You have to justify it somehow, like in your paper or, you know, or an analytical report. So now that we know the heuristics, you know, when to remove them and when not to, let's see how to go about that. Jackson, I see that I'm approaching the 20 past. Maybe I'm gonna make a pause now before we transform the incorrect values into missing values, and hopefully we'll have some more time to push through this rest of the content. So let's go back to your pretty faces. Is there any question so far or comments apart from the noises on the background? Can you actually hear with that background noise? I know it's very annoying, but is that okay? You can still hear my voice? Okay, cool. All right, let's push a little more. Maybe Jackson remind me when we are 5 minutes from the half hour. So now what we want to do is, create a data set that filters the values in this range, so in the middle. So the values that are common, and excluding all the variables, the values that are not common, the ones that are unusual. So the way we can do that is many ways, but one way is to use the function between, which dplyr knows about. It belongs to that package. So we say, okay, take the variable y and pick the variables between, in this case, 3 and 20, which, you know, just by eyeballing the plot are more or less the values that surround the useful data. So we just pick those rows, the rows that where the variable y take the values between 3 and 20, and all the rest we just remove. So with that, we're going to be creating this Diamonds 2 data set, and we're going to be working for the rest, I think, of the lesson with Diamonds 2 or other flavors of it. So that is how you could probably remove the entire rows, but that is not a very good idea often, because because one variable has, incorrect data, it doesn't mean that other variables have incorrect data. So in this case, when I show you the variables x, y, and z, we notice that, some mistakes were in some cases in the 3 of them, but there were many other variables which hold information that may be valid. So like removing the entire row, like in this way, may not be useful. Also, because if you do that with all the missing data, sometimes you will end up with no data at all, or with very little data for the analysis that you need to do. So instead, we are going to not just drop the rows, we are going to just transform those specific values into arrays. So this is how we could do it. So we take the diamonds data set, and then we mutate the variable y, and we're going to be using if else. So if else is this function that takes a condition, in this case the condition that we noticed before. If the variable y is less than 3 or more than 20, then transform those specific values in missing values. And if it's not true, so basically the values that are outside that range, the ones that are in the middle of this distribution, then just keep y. So I'm going to say that one more time because it didn't come out very eloquently. So if the values of y are less than 3 or more than 20, then replace those values with an a. If not, then just leave y as it is, as y. That's what this call is doing. So we are overwriting the variable y with this new, basically this new variable that is overwriting it. So we're going to run that code, and now our data set diamonds 2 that has not dropped the column, the entire rows. It just has transformed the incorrect data into missing data. Okay, so now we're going to plot that in a different way. We're going to be using that diamonds 2 dataset that we have just created that contains those missing values that we injected where the data was incorrect. And we are going to be using, in this case, a scatter plot as opposed to a histogram that we did use before. We're going to just plot the 2 different dimensions of diamonds, x and y. So the way we do a scatter plot is with a function geonPoint, because the scatter plot is just a bunch of little points. So let's run that and see what this looks like. And notice how we get a warning that says remove 9 rows containing missing values. I don't know if you pay attention, but before that unusual data set contained 9 rows. So those are the 9 rows that we have now transformed into missing values in the variable, specifically in the variable y. So that's why we get this warning from ggplot2 when we create that scatter plot that those 9 values that contain missing data have been dropped. So now the plot does not show those missing values. Okay, we have 5 more minutes to go, and I think I could probably push through these last 2 chunks of code that I want to show. But before I do that, I'm going to make another pause here and ask if we have questions or comments.
Maybe I have a more general question to you using mutate in combination with if-else. I was just reading today that there is also a case when function that does a similar thing. What are like the differences between them? Which one is preferable to use?
Perfect, great question. Yes, yeah, there is a couple of ways in which you can do something like that. And if else is, so the two functions do the same thing, but the syntax is different. If else is useful when usually you want to create when you want to consider just one condition. So in this case, there is only one condition, the condition or 2 combined. So the values of y are less than 3 or greater than 20, then do this or that, and that's kind of simple. But then if you want to say, okay, if the values are less than this or greater than that, do this, and if they are in between this and that, then do that, and if they are that and that other thing, then do this other thing. So when there is too many conditions, if else doesn't scale up, because you kind of end up nesting conditions inside other conditions, and your head kind of just gets totally lost. It's super hard to read that code. And case when, the magic of it is nothing else than syntactic sugar. So the way you express the conditions scales up really well, because you express them not in a kind of nested way, but in a kind of stacked way. So I'm not going to cover it now because I wouldn't have time. But if you go to the help file of case when, you will see how, you know, the conditions are always expressed on the right hand side of a tilde symbol, and then on the right hand side you say what you want, and then you can add as many conditions as you want, infinite, and you can still read it, because each time you focus on one line, and each time you understand that line and that line alone outside its context, and then you move to the next one. So just from the readability perspective, case when is a lot more helpful. So then why would you not use it always? Well, because if else is more compact. So when the condition is simple, then case when feels like an overkill. All right, so the last little bit. Yeah, you're welcome. That was a really cool question. The last little bit is this idea. Okay, now we have a data set that contains missing values, and now we want to convert them into a logical variable, because we might want to do something like count them. So it's not easy to manipulate missing data, as you saw before. You know, when you want to plot, for example, the data set, those missing values were automatically dropped by ggplot2. So how could you then, you know, use ggplot2 to plot something that contains the missing values? Okay, the trick is to transform the missing values into a logical variable. Basically, you ask a question, right, to the data, like, is the data missing, yes or no, right? So now you convert the missing data into a yes or a no, basically. So to be more correct, it could be the missing data will be a true, because the question I'm asking here is if it is missing. And the way I rephrase that is with the name is error. So because we identify that the missing data has a meaning here, I think it's more informative to say, okay, it's not just missing, it is an error. We already thought about that, and we capture that thought into the name of the column, a new column that is called is error. So now I'm going to take the dataset diamonds2, and I'm going to mutate it to add a new column that I'm going to call is error, and it's just going to have a true where the values of y are NA. So there is this function is NA, which allows us to do just that. If the value is NA, then returns true. If it's not, returns false. So that way now we have this diamonds3 dataset that has truths or falses in as values of the variable is error. So with that, we can now create a bar plot similar to a histogram, except that we now you know, don't want the function to create the count inside the count. You know, we just want to see the absolute numbers that the variable contains. So here what we're going to do is we're going to pass to the x-axis the values of is error, right? And this is going to be our histogram, our bar plot. It has a problem here though, a visualization problem, which is the same that we had before. Now the number of observations that are not errors is so large, so basically the column that belongs to false is so large, in the order of, you know, like 50,000 or close, that the few 9 observations that are errors are so small that they don't show up in the plot. So we now know the trick. We are going to reuse it here. So first, you know, let's remember how many observations we had that had errors or not. We can use the function count from dplyr that will count, you know, truths as ones and falses as zeros. So it's going to sum, you know, the numbers of truths, and it gives us 9, and it's going to sum the numbers of falses, and it's going to give us 53,000 or so. So we need to zoom in into that plot, maybe with the trick that we learned before with Cartesian, and we're gonna just focus on the first 100. You know, yeah, we're gonna focus on the 100 units on the y-axis, but with the xlim argument. So doing that, and now lets us see, you know, because now 9 missing values or 9 data entry errors are more comparable to, you know, these 100 observations. Now we can actually see them. They were all the time there. It's just that we couldn't see them before because of a scale problem. Okay, so that covers the lesson today. I'm a little over time, but maybe if people want to stick around and have some questions, please go ahead and make your questions or comments now. Maybe to wrap up, what I'm going to do is I'm going to go back to the objectives. So what we have covered today is unusual values and missing values. We first explored outliers, the idea of unusual values, both analytically and by zooming into a plot. Then we decided, you know, by thinking, we decided that those values were data entry errors. So we transformed that into missing values just in those values without dropping the entire row, because that could lead us to having no data at all, or too little data to do something meaningful. And then we also wanted to manipulate, to plot, to count, whatever, those missing values. So we couldn't do it as they were. We transformed them into a logical variable, where true was the value of the variable is error, and false when the error where the data was valid. And we used that to create a bar plot. That would be the way to wrap up the session. Any last departing comment or note or question? Okay, then I thank you very much and see you next time.
Thank you, Mauro.
Ciao, ciao.
Thank you, Mauro. Bye.